So let's go ahead and look at an example of a proof by contradiction. So I have put up here the method by which a proof by contradiction proceeds. And what we want to do is apply it to this particular example. Show that for every theta, that little symbol right there is a theta, think of it as an angle, in 0 to pi over 2, so in that interval of real numbers, sine of theta plus cosine of theta is greater than or equal to 1. So I want to show that this is the case, and I want to argue by contradiction. So as usual, it's extremely helpful, especially for the reader, to declare what sort of proof technique you are using. So to declare that we're using a proof by contradiction, we can say in search of a contradiction, which is declaring that I'm doing a proof by contradiction. And you might see me abbreviate this at some point, ISOAC, in search of a contradiction, just because that's a long thing to write down and I'm lazy. So in search of a contradiction, what do? Well, we assume not the statement we're trying to prove. So we want to assume not this statement. So I've assumed not my statement. And here, since I know how my quantifiers interact with my logical operators, I know how to take the negation of this statement. So I know that if I'm negating a for all statement, what I need to do is flip from this universal quantifier to an existential quantifier. So this is logically equivalent to and then I need to negate this part. So sine of theta plus cosine of theta is not greater than or equal to 1. So this tells me that I'm assuming there exists some theta in the interval between 0 and pi over 2, such that sine of theta plus cosine of theta is less than 1. And now, to follow our proof by contradiction, somehow we need to derive a contradiction from this assumption right here. So it might be helpful to go back and think about our trigonometry. So you might recall we had our unit circle with our x and our y axis here. And if you had some sort of angle theta, then, well, the value of this point right here on the x-axis is cosine of theta, and the value right here on that y-axis is sine of theta. And this particular theta that we are supposing exists lives in the interval between 0 to pi over 2. So if you remember radians, 0 to pi over 2, that's this part right here. Zero to pi over 2. So how does this help us? Well, since we know that this theta exists in that interval, we know that sine and cosine are only ever going to take values on this part of the x-axis or on that part of the y-axis. And what's so special about those axes? Well, notice over here, x is positive, and over there, y is positive. Well, that's a nice thing to know, so let's go ahead and jot that down just because we know it's the case. So it gives us a little bit more information to work with. And that information that we have to work with, since we know that this is non-negative and that is non-negative, And for that particular theta, we also know that their sum is less than 1. That means that we have 0 is less than or equal to sine theta plus cosine theta is less than 1. I got this right-hand side of the inequality from that part, and I got this left-hand side because I know that these two are positive or non-negative, so their sum also has to be non-negative. So where do we go from here? Well, remember, we're trying to derive some sort of contradiction. And you might recall from your different trig rules that there's something special that happens whenever we square sines and cosines. And why would I think about doing that? Because I know that if I square, for instance, this expression, 0 squared is still just 0 and 1 is 1, so it's not going to change any part of my inequality. This is that creativity part of trying to derive the contradiction, because you don't know specifically what contradiction you're trying to derive. So you gather the facts that you have, and then you keep on trying different things and following your nose. So I'm following my nose here, and I'm going to go ahead and take this expression and square it. Zero squared is still 0, less than or equal to, and then squaring the inside here. And then 1 squared is just 1. And now, oh, I see something interesting. Sine squared plus cosine squared. So, recall sine squared of theta plus cosine squared of theta equals 1. So if I take this part of my expression, what I'll end up with is sine squared plus cosine squared. That becomes a 1. I still have this plus 2 sine theta cosine theta, and it's all less than 1. Well, I see a 1 on this side and 1 on that side, so let's go ahead and subtract 1 from both sides, and that will leave me with 2 sine theta cosine theta is negative. Well, it's negative. Well, didn't I assume somewhere? Yeah, we know that sine of theta is non-negative, and cosine of theta is also non-negative. So what we've been able to show is that these two things can't coexist together. This here implies that one of either cosine of theta or sine of theta is negative, because when you multiply them together, you get a negative number, and that too there is positive. So this statement and those statements cannot coexist together. That is a contradiction. You cannot have that one of them is negative and they're both not negative. Therefore, this is our contradiction. And then we can go ahead and conclude our proof, because we've been able to derive a contradiction. This part, that was our big old contradiction. You can't have this statement existing simultaneously with that statement. So if I were to flesh this out a little bit more and turn it into a proper proof, you could add a few words here and say, this implies that expression, and then that expression. There we go. So now we've completely finished it out. We've filled in all of our details, and that completes our proof by contradiction. So as I mentioned beforehand, these proofs by contradiction, they require some creativity. One way to help you with figuring out that creativity is gather all the facts that you know. So here I was gathering facts about sine and cosine, and it actually turned out to be very crucial to my proof because I use that to be able to derive my contradiction.